The first speaker will be Julien Lesgourgues, and the title of his talk, Could Cosmological Tensions Hint at Non-Standard Dark Matter Properties? Please, Julien.
Yes.
Now.
Good morning, and thank you for the introduction. So the tensions I will be talking about today are the famous Hubble and S8 tension. So you have all heard about them. The Hubble tension is related to the measurement of the Hubble rate today by the method of distance ladders, in particular supernovae that are calibrated to Cepheids, that are calibrated through the parallax method. While S8, as you know, is a parameter that quantifies the amplitude of the matter power spectrum at some scale and some redshift. And it's measured in particular by weak lensing surveys. In the middle between these experiments stand the results reported by other techniques like the CMB, the baryon-acoustic oscillations, which are not directly probing these parameters, but for which these parameters can be reconstructed by an extrapolation after assuming a given cosmological model. And the big problem that you have all heard about is that if you assume lambda CDM as the reference cosmological model, then the value of H naught that you infer is in 4 to 5 sigma tension, with distance ladder measurements from shoes, maybe completed by other experiments related to strong lensing, and is in 2 to 3 sigma tension with measurements of S8 reported by essentially all weak lensing data. So the first level of tension is really worrying. The second level sounds like very weak, 2 to 3 sigma. You would say there is nothing to discuss. But these experiments are never combined with each other. And the intriguing point is that they have all been reporting this 2 to 3 sigma tension in the past 15 years, which means that I tend to believe maybe even more in this tension than in the Hubble tension, which seems larger, but is dominated by essentially one experiment. So these tensions are intriguing, and of course, we are not completely sure that they cannot be solved by a better investigation of systematics. People have been criticizing the assumptions of the Schuss collaboration. Usually every time the Schuss collaboration came back with a convincing answer. So there are criticisms, but it's really not clear so far that they are founded and that there is something wrong with the Schuss data, although this should be really followed up. On the side of S8, people tend to agree that the weakest points are redshift errors when you try to infer the redshift of the lensing galaxies in a photometric survey. This is a very difficult problem, and people have a hard time agreeing on a good method, and this problem will only be solved when we will have much better data from forthcoming surveys like DESI, Euclid, LSST. People also put in question systematics in the CMB, although in my opinion it's really very hard to find new important systematics that would really change the CMB predictions. So then one thing we should consider is a possibility that these are really indications for deviations from lambda CDM, maybe due to some new ingredients that would have small effects, maybe related to dark matter, which is a topic of this conference. If not, it could have to do with dark energy, with modifications of gravity, with new physics like important primordial magnetic fields, etc. Or maybe we have to put in question the Friedman model on the larger scales, because we don't want to touch the smaller scales, which are so well tested with the CMB. I will come back to this at the end. So I will take this point of view and do a review of, for instance, what could solve the S8 tension. This one is the easier one. The Hubble tension is really very, very delicate to solve. For the S8 tension, there are ideas. I should start by saying that the simplest ideas would not work. If you just say, I'm going to assume a large enough value of the standard neutrino masses, and this will decrease the power in the matter power spectrum and solve the S8 tension, This would obviously not work because you would need a relatively large value of the total neutrino mass of the order of something like 0.3, 0.4 electron volts. Then these neutrinos would become non-relativistic early, close to recombination, and they would spoil the fit to the CMB through the early integrated Sachs-Wolfe effect or CMB lensing. So you need to be a bit more clever. People thought about decaying dark matter model. If some of the dark matter disappears, then maybe you have less power in the matter power spectrum today. And this is also very difficult. If dark matter decays into electromagnetic components, then there would be exotic energy injection in the photons. You would see it through the CMB spectrum. If the decay is into neutrinos or the dark sector, there are still gravitational effects like lensing or the late integrated Sachs-Wolfe effect. So there were very nice work by our chairman and collaborators on this a few years ago. I think everybody would agree probably nowadays that with current data, when you take all current data into account, a simple model of decaying dark matter is too constrained in order to solve the S8 problem. So you need to be a little bit more clever, but that's really doable. Many modified gravity would do the job, but of course modified gravity is a Pandora's box that maybe you don't want to open. If you do it with some F of R gravity, for instance, you can reduce the growth rate of dark matter, and that would solve the S8 tension. You could imagine that dark matter has feeble interactions, and that's interesting because now it comes closer to the work of dark matter model builders, or people trying to think about what are the ingredients in the dark sector. So if you have a small scattering rate between dark matter and especially relativistic particles like photons or dark radiation within observational bounds from particle physics, then still you can have a collisional damping effect that could solve the S8 tension. This would work. You could have a mixture of cold and warm dark matter that would reduce a little bit the matter power spectrum on small scales. You could think that you have decaying dark matter, but not its in simplest version. In order to have a workable model, you would need to assume that your cold dark matter is relatively long-lived with a lifetime much larger than the age of the universe, such that only a small fraction has decayed by today. And you should assume something like a two-body decay in which each decay of a dark matter particle produces a massless particle and a massive daughter, which has a mass a little bit smaller, but not much smaller than the original dark matter particle. So this also works, and for instance, the authors of this paper here have tried to connect it to other problems in particle physics, like the xenon one-ton anomaly. A model I find really cute is a model of cannibal dark matter. Well, it's not a model, it's something generic that would happen in many dark matter models, in which you don't have a symmetry that imposes a number conservation of the dark matter relic. And then you can have non-conserving processes, like for instance, 3 particles decaying into 2 particles through an effective 5-leg vortex. And this has a very interesting phenomenology at the level of cosmology, because it means that there is a regime between the radiation-like regime and the relativistic-like regime and the non-relativistic-like regime. You have an intermediate regime that people call for fun the cannibalistic regime, in which dark matter eat up each other, and this makes them become warmer, and because of their temperature and velocity dispersion, they behave a little bit like warm dark matter. They suppress the growth of structure on small scales, and they can solve the S8 tension. So there are lots of ideas that could be maybe connected to some particle physics, even maybe testable in the laboratory if we are very optimistic. And importantly, also, these models could have a connection with the famous cold dark matter crisis. They could solve the problem of cold dark matter on even much, much smaller scales than the one needed for S8. Unfortunately, or fortunately, I don't know, solving the Hubble tension with just dark matter or cosmological model building is a very, very difficult exercise. It's much more constrained, and if there are hundreds of models that have been proposed, the whole landscape, and probably these models can be classified in 3 categories. The first category, I will not spend much time on it because in a few slides I will tell you that I believe that this does not work, is to change the late time cosmological evolution. In particular, what people try to do is put a new ingredient that would really change qualitatively the expansion rate behavior between very small redshifts, which are important for the measurement of the Hubble tension, for instance, by shoes, and slightly larger redshifts, which are very well tested by baryon acoustic oscillation data, or the high redshift supernovae, not the one used for measuring H0, but the one used for probing the acceleration of the universe. And I call them the uncalibrated high redshift supernovae, because in this category of supernovae, usually people don't try to calibrate the luminosity, absolute luminosity of the supernovae. They leave this as a free parameter because they are more interested in the curvature of the luminosity distance versus redshift relation, independently of the calibration of the absolute magnitude. So you have here two groups of data, and the goal is to feed them simultaneously by having something like, for instance, a hockey stick equation of states, which leads you to something like phantom dark energy at small redshift. It sounds very ugly and unnatural. However, people have shown that you can do it without violating the weak energy principle, but it's very constrained model, and I will show that all these things are in fact probably excluded when you consider all data. The second avenue consists in increasing the effective number of relativistic degrees of freedom, because this is a well-known way to make a large value of H0 compatible with a CMB. You know that the CMB in particular measures the sound angular scale given by the ratio of the sound horizon over the angular diameter distance. And if you have a large number of effective degrees of effective degrees of freedom, then you can predict a different value for the sound horizon. And then to make this value compatible with the CMB measurement of the angle, you need to change the Hubble value and for a higher value. So this is promising, but there are many difficulties associated to it, because when you increase N effective and H0, even if you preserve this angle, there are lots of subtle effects that occur at the level of perturbations, and that may spoil your fit to the CMB. You increase the silk damping, you shift the acoustic peaks in both amplitude and scale due to an enhanced neutrino drag effect. And so you need to counteract these effects if you want a workable model, and then you need to enter into the fine art of cosmological model building at the level of the evolution of the perturbations of the different species. And you are driven to relatively complicated model, which very often involve new interactions in the dark sector and or in the neutrino sector, because these new interactions are a way to change the evolution of perturbation through collisional damping, or by coupling a non-clustering species to a more clustering species, you can enhance the growth of its perturbations. So you have to play with all these effects. Some models that have been relatively successful a few years ago, since 2-3 years, were self-interacting neutrinos with a very large self-interaction rate, or dark matter scattering on dark radiation particle, which can be motivated by relatively simple constructions for the dark sector. In these models, the neutrinos or the dark radiation does not free stream, and this helps to solve this acoustic peak shift effect or this extra silk damping effect a lot. So I will tell you in a few slides if these models are still successful. The third avenue is when you try another way to change the early cosmological evolution, different from using N effective. And in particular, there are different ways to change the sound horizon at early time, not playing with N effective, but with other components, like some early dark energy components, or by shifting the time of recombination, which is doable if you have inhomogeneous recombination triggered, for instance, by some strong primordial magnetic field that would induce small-scale inhomogeneities, or if you assume a running of the fundamental constants that are responsible for recombination due to some, for instance, dilaton in string theory, and that could cause a drift of the fine structure constant or the effective electron mass of hydrogen atoms. And okay, these models are a bit less constrained, so it's a bit easier for them to pass all the tests because they modify physics at early time, which is less constrained than at late time. But then precisely for this reason, you could say that they are more ad hoc and more difficult to connect to other problems in physics. So how do you decide which models work and which does not? Well, you can do like the heroic effort of a group of people led by Eleonora de Valentino. They have compiled all existing proposals for solving the Hubble tension. It's a tremendous work because there are more than 100 models, and most probably you cannot read all the names on these slides. Each line here is a proposal to solve the Hubble tension and the corresponding prediction for H naught. However, this is just a compilation. It's not a reanalysis. And when you look at the details of these models, you realize that each author have published their prediction for H naught with maybe a little bit of bias, maybe cherry picking the data that are good for their models. So also another issue is that very often when people combine information from large redshift supernovae and shoes, they don't do it in a fully consistent way. It has been understood only recently how to combine them in a fully consistent way. So this motivated us with a group of people from Montpellier and Amsterdam and Aachen to look not at the 100 models, but just to select some typical models out of these, and to do a fair ranking on these models by doing our own analysis in a blind and unbiased way using the same data and the same statistical tests each time. And I'm going to show you the results. Okay, I'm going to explain this plot. This plot is obtained by comparing a selection of models that I will detail to Planck 2018 data completed by robust data from bioacoustic oscillations, high redshift supernovae from Pantheon. And then in order to do a test of the resolution of the Hubble tension, you also use the shoes data. And you compute this delta AIC, which is a variation in the Akaike information criterion with respect to lambda CDM. You are probably familiar with this because it's mainly popular for people who do frequentist analysis, so for particle physicists. So this delta AIC is a delta chi-square of the best fit of the extended model compared to the lambda CDM model, corrected by the effect of the number of free parameters in order to take into account Occam's razor. We established by a small statistical calculation that a model that would be really a convincing way to decrease the Hubble tension to an acceptable level would be a model that would have a delta AIC above the threshold here of about 10. There is a little reasoning behind this number. And you see that very few models succeed. And if we summarize, all the late time models, which are here, which are models with late dark energy, with a funny equation of state, or with a late decay of dark matter into other species, all these late models fail to solve the Hubble tension. It's funny because if you look at individual papers on these models, sometimes you have the impression that they are the best on the market, that they fit the Hubble tension very well. But by applying this blind analysis, putting all this data together, we find that they are in fact among the worst ones. Then the models that do not use extra relativistic species, but are based on other modifications of the early time cosmology, tend to do a good work. In particular, this early dark energy model, I'm not particularly fascinated by it, but it's the one that offers the best fit. It's able really to lead to a large Hubble rate without spoiling all the details of the fit to Planck, the polarization data, small scales, everything is very successful. The other models that are relatively successful are the models that shift recombination by invoking, for instance, these primordial magnetic fields to have recombination taking place earlier due to small scale inhomogeneities, or these models with a drift of the effective electron mass between the time of recombination and today. Disappointingly, the model based on extra relativistic degrees of freedom, which were really my favorite ones because they are the ones that you can connect in the easiest way to real particle physics, don't do such a good job, including models that I defended in the past, like dark matter interacting with dark radiation, these self-interacting neutrinos do pretty bad because they are a bad fit to the Planck 2018 polarization data. Models with self-interacting dark radiation do not work very well. The only model in this category that works well is a model based on a Majoron-like scenario. And since it's doing quite well, and I think it's based on reasonable physics, I will spend a couple of minutes explaining what it's about. So I did not contribute to this. It's a work by Escudero and Witt, but of course, similar to many other proposals for a Majoron idea. As you know, the Majoron would be like, the Majoron idea is to introduce a kind of Higgs-like mechanism in order to explain the neutrino masses, and you can also explain the lepton and baryon asymmetry in the early universe. So the Majoron phi would be the pseudo-Goldstone boson that remains after the spontaneous breaking of the global lepton symmetry. And it is coupled to active neutrinos through some Yukawa couplings. And these models can have a very rich cosmological phenomenology. And what is particularly relevant for us is what happens at late time, at recombination and after. And if you assume that the Majoron mass is of the order of the electron volt, then at the approach of photon decoupling and recombination, the interactions between the Majoron and the active neutrinos can rethermalize the Majoron that thermalized the first time in the early universe. They rethermalize at the approach of decoupling and contribute to N effective, which is very useful for solving the Hubble tension. But at the same time, because of these interactions, the neutrinos cannot, the ordinary neutrinos cannot free stream because they scatter on the Majoron. And by killing neutrino free streaming for a while, you have a very nice effect on perturbations, which is close to the effects I described before. It helps solving the silk damping and neutrino drag effect, and you get a good fit to the CMB data, even with large NF and large H0. And then at temperature smaller than the EV scale, the Majoron decays into active neutrinos, and the neutrinos free stream again, like in the standard model. So you can decide if from a particle physicist point of view you like this model or not, but it has a very interesting phenomenology for cosmology, and it succeeds in adjusting all these little subtle effects in the right way in order to make CMB and all other data compatible with a relatively large value of H0. So I discovered this model only recently, and I must say I was impressed. So here you see the fit, the value predicted for H0, and at the same time for MB. MB is a parameter related to the calibration of supernovae, and so the results from shoes can be expressed in a more direct way as a result for this calibration, supernovae calibration parameter, more directly than a result for the Hubble parameter. And what is interesting is that the lambda CDM model cannot achieve large value of H0 and this calibration parameter, which are indicated by shoes, while the model with a Majoron can increase H0 really a lot. All right, so now can you solve both tensions at the same time? It seems very difficult. I've not seen a good model trying to solve both tensions at the same time. Of course, I'm not sure that both tensions do exist, but if we take the point of view that they are true, it's very difficult, and because most models tend to ease one tension at the expense of making the other one worse, either a bit worse or much worse. So it's very difficult to build a model that would simultaneously increase H0 and decrease S8. I'm aware of a few exceptions, although they don't solve the tensions completely, but I can mention them also because they can be connected to dark matter model building and dark sectors. So if dark matter interacts with dark radiation, I told you previously that it cannot solve the Hubble tension very well, it can only ease it. But at least it goes in the right direction of increasing H0 and decreasing S8. So here you have the values of S8, and the purple band is what weak lensing data would like. Here you have the value of H0, and the red band is what the Hubble shoes would like. The lambda CDM model is here. And if you assume a small interaction between dark matter and dark radiation, caused, for instance, by a dark gauge interaction in the dark sector, then you see that you can have at the same time significantly larger H0 and a slightly smaller S8. So I didn't list this into the list of models that are a convincing solution to the Hubble tension because this doesn't go high enough on the right. But if you would try to see which model solve globally the two tensions, then probably this model would still be one of the best. And you could make it even better if you assume that your dark matter interacts with dark radiation and ordinary photons at the same time. Because interaction between dark matter and photon is one way to very efficiently decrease S8. From a model building point of view, these models are not ideal because it's very difficult to assume a small coupling between dark matter and photons without having an even larger one between dark matter and baryons, which could be excluded by laboratory constraints. But there are proposals. Neil Weiner has a model of mealy charged dark matter that would couple dominantly with photons. It's possible. And if your dark matter would couple at the same time with photon and dark radiation, then you can really achieve a relatively large H0 and a really small value of S8. And you could think this is completely crazy. Maybe it is. Maybe it's very fine-tuned. But okay, you could say that dark matter could interact with a dark photon. The dark photon would be the dark radiation. But if there is a mixing between the dark and visible photons, then dark matter would indeed have small interaction rates with both photons and dark radiation. So maybe it's a bit crazy, but it's not desperate. Okay, more studies are required in view of solving both tensions. For instance, I praised this Majoron scenario before. This one has not been yet investigated, taking into account the active neutrino masses, because this raises technical difficulties at the level of modeling cosmological perturbations. But if they could be solved, then maybe this Majoron model would solve both tensions at the same time. All right, so now my conclusions. I've changed a bit of opinion on these tensions since I've done this recent work with Montpellier and Amsterdam group, because really I see that it's very difficult to have a convincing theoretical explanation to these issues. So I think I would mainly hope that one or both tensions get solved by systematics, but it will take time before we can clarify these issues. They are really difficult issues from an observational point of view. We really need much better data. We need to wait a few more years. But this would preserve the beauty and elegance of the simple lambda CDM scenario. If this is not the case, I should say, in a way, the fact that it's so difficult to explain these tensions is a bit reassuring, because I'm sure that some people could have said a few years ago, oh, cosmology, I don't really believe this fits, because whenever there is an anomaly in the data, they can immediately come up with a model that solves the anomaly. You see, it's not true anymore. We are really in this era of precision cosmology. We have to explain slightly anomalous values of two numbers, and it seems to be extremely difficult to find a model that can escape all bounds and fit all the data at the same time. So it shows that you cannot do whatever you want with cosmology. And if we do find a really working solution, then this will be one of the only solutions. So there is still some predictivity in this game. And if these tensions are really settled and not due to systematics, a good thing is that the previous models that I mentioned, that would be the best current ways to solve the Hubble tension, they make predictions already at the level of future cosmological observations. All these models of early recombination with primordial magnetic fields, of the Majoron model, the model with early dark energy, you might find them a bit crazy, a bit ugly, but at least they make very precise predictions on what would the CMB polarization or matter power spectrum look like. And in these observables, there is still a lot of information that we have not yet observed, and we are going to observe it in the CMB thanks to the Simons Observatory, CMB stage 4, Lightbird. In large-scale structure, there will be huge progress with DAISY, Euclid, LSST, and these will be opportunities to test these models. And for instance, if what early dark energy is currently predicted was precisely observed, we would have to admit that this might be the solution. So there is still some predictive power in these models. Would be even better if these models could tell you about new particle physics and about some tests we could do in the laboratory about this dark matter scattering rate, for instance. I'm a bit less optimistic now than 2 years ago because I see the difficulty of these models to solve the Hubble tension, but it's still a possibility. And finally, maybe if these tensions are there, maybe all these models are not very convincing, very fine-tuned, relying on very non-minimal assumptions from the particle physics side, and maybe after all, it's more elegant to revisit the Friedman assumptions, assumptions of a Friedman model. And this has been questioned recently by several people who notice that maybe we should keep all the benefits of the Friedman model when we want to describe small scales, corresponding to observations in the CMB below a multiple of L, something like L bigger than 100. But for very large scales, maybe there are some departures from homogeneity. And we were convinced a few years ago that this was not the case because the fit to Planck data works so well. But I'm not really so sure anymore. Some people like Fossalba and Gastanaga have done a very interesting analysis in which they try to measure the cosmological parameter not from the full Planck map, but from small regions of a few angular angular square degrees. And they find something very interesting. They find that when you try to fit, for instance, here H naught or the lambda CDM parameters in different directions, you get huge variation if you look in different directions. There are big zones that would indicate a large Hubble parameter, big zone that would indicate a small Hubble parameter. You do expect some scattering when you do this kind of experiment. You do expect some scattering. What is intriguing here is at first, it's not random scattering. There are large coherent regions returning some values of the cosmological parameters and other large coherent regions returning other values. And moreover, if you look at these kind of diagrams, not just for the Hubble rate, but for all the other parameters of the lambda CDM model, they all lead to exactly the same regions. So this could be an indication of deviation from the Friedman model on very, very large scales, up to, I don't know, the hexadecapole or something like this, or maybe not even. And there are also people questioning the fact that the dipole that we measure through the CMB seems to be in mismatch with a kinematic dipole that you reconstruct by when you try to estimate our local velocity with respect to the frame of galaxies or quasars at a redshift of 2, 3, 4, 5. So this might be an indication that the CMB dipole that we observe is not only due to our local velocity, that there are large bulk flows, large-scale inhomogeneities, and maybe these aspects of the Friedman model also need to be revisited and would offer a way to solve these tensions without touching the simplicity and beauty of the lambda CDM model. And okay, I will stop there. Thank you very much.
Oh, thank you, Julien, for very interesting and very comprehensive talk. Really. Now, questions. I see raised hands. First, Peter Tinekov.
Okay, Julien, thanks for the talk. You have been talking a lot about modeling. So I wonder, on the experimental side, what needs to be measured to sort it out? You said we should wait for 3 to 3 years. Wait for exactly what? What are the crucial data we need to sort it out?
So I think from the weak lengthening side, it's a bit easier because the redshift of the, so in the future, we will have a much more precise instruments for measuring the redshift of the galaxies that are used for the cosmic shear analysis. So I think that, for instance, Euclid is supposed to be launched next year. Okay, this is very optimistic. Maybe it will not be next year, I'm not sure, but it will be in very few years. And I think there, this issue of the photometric redshift errors can be addressed in a convincing way. So I think this should be settled. For the distance ladder measurements, it sounds a bit more difficult because there will always be these uncertainties on how much Cepheids are different from each other, and is there a kind of bias introduced between the supernovae that we see at large distance and at small distance that we use for calibration, because some live in a star-forming environment, some not. So there are all these bias issues. So I'm not sure what we need. Of course, people advertise that the measurement of standard sirens with gravitational waves would be a very good tool. So indeed, if you use something like LISA or the future Einstein telescope to accumulate hundreds of measurements of standard sirens from black hole and neutron star mergers, then you will get a measurement of the Hubble parameter, which is more precise than what we have today. But for this, you will have to wait for a long time.
It's not 2-3 years. No.
No, that's not 2-3 years. My 2-3 years was more referring to the S8 tension. This, I think, can be done in 2-3 years. Yeah, for the Hubble, I think we have to wait maybe for more time.
Okay, thanks.
Next question, Andres.
Yeah, Julien, thank you very much for this inspiring talk. I have a question about this Majoron. So, what would be the best prospects to look for this in a laboratory, to search for it for a laboratory? Can it be so? You said it should have a mass of electron volt scale. So, what are the necessary interactions which you need to solve the problem, and what could be the couplings to the photon or so
yeah
on?
Yeah, I'm sorry. I discovered this model very recently. I didn't work on it myself, and I've not yet studied the potential for laboratory constraints. I know that it really makes prediction for the CMB polarization that are within the reach of an experiment like CMB stage 4. But I would prefer to refer you for the paper for the future.
Okay.
I'm sorry, I've not studied this.
Thank you.
Yeah, Julien, just taking my position as chairman, I'd like to maybe defend a little bit decay in dark matter model on which I was working. No, this Majoron isn't, can I view it as a just modification of decay in dark matter? No?
Yes, you can certainly. You can certainly. It's no, sorry, no, because the Majoron is never playing the role of dark matter. It decays when it becomes non-relativistic.
Yeah,
so
yeah, okay.
Yeah, so it's more like
it's very light. I forgot it. Very light.
Decaying into ordinary neutrinos. So really, the important role of this Majoron is at the level of the perturbations. It's like a way to have neutrinos free streaming at some time and not free streaming at other times. It's more related to this. The decay is not so important, in fact.
Yeah. Next question, Inar.
Yes. So thank you very much for the nice talk. When you were comparing the models, you were using this Akaki information criterion, AIC.
Yeah.
Right. But so if you were to use, for example, Bayesian information criterion, which has a larger penalty for more parameters, would the picture change? Or?
Yes, it would change. And okay, in the paper that we have not yet published, we use, in fact, 3 criteria, and we quantify the goodness of fit on the basis of 3 criteria. We don't use Bayesian evidence because computing the Bayesian evidence is a technically difficult problem. You can easily do it when you are studying 1-2 models, but we have all these, we have something like 16 models. Computing the Bayesian evidence ratio for the 16 model is a bit too expensive computationally, but you can just evaluate the tension, for instance, by looking at the posterior on H0 without shoes, comparing with shoes, quantifying the tension from this. This is not also very easy because usually these posteriors or on H0 are not Gaussian. So you cannot just use a simple formula of difference of the means divided by a square root of sum of squared errors. But we also provide these criteria for comparison, and they give different results indeed. And so, for instance, some are more favorable to early dark energy, some are more favorable to the Majoron model. So yes, sure, there are different criteria and they give slightly different results, but not at the point of completely changing the conclusions.
I see. But there is no like unique way to determine which criteria to use, because, for example, there's BIC, which is the same as AIC, but the penalty is not the number of extra parameters, but the number of extra parameters times log of observational points. This can change.
I don't think there is a unique way. In the same time that, in the same way that nobody can agree whether the Bayesian should completely discard the frequentist point of view or vice versa. There are always different approaches, different ways to formulate the problem from the point of view of a statistician. So I don't think there is a unique way. We have discussed a lot about the merits of these different criteria, and given that we cannot compute Bayesian evidence, we believe that this is the second most reliable, but this can be debated.
Mm-hmm. Okay, thank you very much.
Do I see another question from Edward Vasa? Yes.
This was just a quick follow-up. I was wondering why the distribution of the uncertainty in the Hubble parameter was non-Gaussian. Why is that?
So, according to the information we have from an experiment like shoes, we don't have access to many details, and we have to model it as Gaussian. Instead, when we fit models to the data, Planck plus BAO plus Pantheon, to the cosmological data, then we reconstruct the posterior on H0 from a full Monte Carlo analysis. And because these models often have parameter degeneracies, the contours are not elliptic in parameter space, and you can have strong non-Gaussianities. For instance, the posterior of this early dark energy model is very asymmetric, with a much longer tail towards large H0 than towards small H0. So
okay. Yeah. Actually, so would that be model dependent or?
Yes, sure. Each model has a different, each of these models will predict a different shape for the posterior on H0. Some of them are Gaussian, some are not. And this is really an information that we have. And that but it's not completely obvious to use it in a simple way in order to quantify the tensions, but it's doable.
Okay, thank you.
I don't know. It's very important subject, and I'm sure we still have questions, and I myself have some questions. In fact, we have some time because introductory was supposed to last for 15 minutes or 10 minutes. And then, yeah, maybe. Julien.
Yeah.
There was recently one paper on the Hubble constant tension in the supernova Pantheon sample, where they see change of H0 in redshift. Do you know this paper? Is it included? Are those data important, or errors still very large to have any effect?
Is it a paper by Motzel and Gubar?
Maria Dainotti.
Sorry?
Maria Dainotti, first author.
No, I'm sorry. No, I don't know this one.
You don't know. Okay.
No,
amazingly, they saw that H0 changes with redshift.
Mm-hmm.
Errors are big, but they see the effect. So might be important in the future, maybe, with better data.
Okay.
They have 1,000 supernova recent catalog and studied it for this effect.
Yeah, it's already difficult to understand.
It's already difficult. Yeah, no, it's very difficult. Yeah, but maybe.
Yeah, I remember the paper. It's a very convolved way to present the result because H is a function of Z anyway.
No. I understand. My understanding is they assume standard evolution and extra change in H0, what we assume a constant. Of course, it's controversial to say that H0 changes with redshift.
I think so. I think it's a very convolved way to say maybe that they believe that the luminosity distance to redshift relation is not exactly the one you would expect in lambda CDM with a plain cosmological constant. That would be, in my opinion, a better way to formulate it. But I don't know how much significant this paper is, and my impression is that when you fit in all these models, when you fit the Pantheon data, you can wonder if the chi-square you get for Pantheon is typically good or bad. And my impression is that it's typically good. It's typically what you expect given the numbers of degrees of freedom. So I don't have the impression that the Pantheon data is telling us to look at something more complicated than lambda CDM evolution at late times. That's not my impression.
But what do you think the weakest data are? Of course, to fit all data, it's very difficult, but which are most weak and fail? I mean, when we were working, say, on decaying dark matter, an obstacle for us was a lensing, CMB lensing.
Yeah.
But CMB lensing by itself is controversial in Planck data.
Yeah, it's slightly.
So which data could fail?
Mm-hmm. So I think what is controversial in Planck data, as you know, is not really the measurement of CMB lensing, the extraction of lensing, but the fact that the temperature spectrum looks like it would be more lensed than in lambda CDM, because there is more smoothing of the extrema of the peaks. And people have called this the AL anomaly, while everybody knows that it refers to a parameter which is not physical. It could be a statistical fluke, I believe, or it could be some indeed systematic effect which is not modeled well enough. But this systematic effect could be totally unrelated to lensing. It could be anything that would contribute to decreasing a bit the maximum of the peaks. I don't know what it is. I see how carefully the Planck analysis was done, how difficult it would be to miss a foreground. So I'm not very worried about this so-called lensing anomaly. I think it's a statistical fluke, and the overall goodness of fit to Planck data is good enough, in my opinion. So I think for me the weakest data here is in this list is shoes. And of course you have also data set that are not included in this list, but this is clearly where I see the biggest number of empirical assumptions and trying to model physics we don't understand by playing with Newton's parameters. So I really think it's a weak point.
Okay, thank you. Yeah, maybe we can arrange some discussion session if there will be more questions and interest in some topics during our workshop. But we have to move on, and thank you, Julien, once again.
Thank you very much.